So number 34 is one of the more challenging problems. What you've got here is you've got an oversized yo-yo made from two identical solid discs, each of mass 2 kilograms and radius 10 centimeters. The two discs are joined together by a solid cylinder of radius 4 centimeters and mass 1 kilogram as shown in the figure. Take the center of the cylinder as the axis of the system. So imagine you've got an axis going straight through the center of that rod going to the other side. Okay, take the axis, okay, with positive torque directed left along this axis, okay. Light string is wrapped around the cylinder, and the cylinder then is allowed to drop from rest. What's the moment of inertia of the system? So we're looking for I in this part right here. That's pretty straightforward. If you remember from your table, the rotational inertia of a disk or cylinder is 1/2 mr squared. In this case, we're dealing with 3 separate cylinders. 2 of them have mass capital M and radius capital R, and the other one has mass small m and radius small r. There's 2 of the big ones, so I put a 2 in front of that. And if you simplify that down, it simply becomes this. mr squared, the 2 and the 1/2 cancel, plus 1/2 small m small r squared. Part B. What torque does the force of gravity exert on this system? Well, this one's a little bit trickier, but remember the center of mass would be right in the middle of this thing, and the force of gravity acting straight down it. Now remember that we assumed that our axis of rotation was right through the center, which would go right through the center of mass. And so B is a little trivial in some ways. The torque is 0. There is no distance between the force of gravity and our axis of rotation. R would be 0. Take downward as is the torque exerted by the tension positive or negative? Now, this gets a little bit more interesting, and I don't like the way this one sort of defined it. But remember, you've got tension acting this way along the string, and you got the force of gravity acting at the center of mass that way. If you solve this one, this is actually a bunch of ones in this case. For C, is the torque positive or negative? Is the angular acceleration positive or negative? And what about the translational or regular acceleration? So this one's acting a bunch of different things. Well, the answer to this one, if you calculated the torque and use the right-hand rule, which I much prefer to their coordinate system, your torque should be pointing out in the negative y direction. So your torque would be pointing this way. And I would consider that to be a negative x direction. And the angular acceleration would also point in that direction. The translational acceleration, this whole thing is going to unwind and begin to accelerate downward. And so your acceleration would be in the negative y direction. I much prefer those coordinate systems than the one that they defined earlier. D. Write an equation for the angular acceleration in terms of the translation or regular linear acceleration and radius. Watch for the sign. Well, if you remember, the relationship between angular acceleration and regular tangential acceleration is angular acceleration times radius is equal to tangential acceleration. So just rearranging it, you get that. E. Write Newton's second law for the system in terms of M, A, T, and G. Well, I'm going to move it over down here. Newton's second law, F net equals MA. What's the net force on this thing? Well, you've got force of gravity downward, tension upward. I'm assuming that force of gravity is larger. So force of gravity on this one is this entire term right here. The total mass times gravity minus the tension is equal to the total mass, which is, again, this thing, the sum of the masses, times A. So this is M, and this whole thing right here, force of gravity minus tension, is the net force. And that's as far as we can take it. F, write Newton's law for rotation in terms of I, alpha, tension, and radius. So for F, Newton's equivalent, F equals ma, becomes torque equals I alpha, just using the Rosetta Stone. Plugging in our torque, it's just going to be the tension times the radius is equal to I times alpha. Interesting, they just wanted in terms of this. We could have actually plugged in the solution we had for I up on top here, for I down here, but they didn't want that. Now, H. Oh, sorry, missed it. G. Eliminate alpha from the rotation law and from that and find a symbolic some expression for the acceleration. All right, so for G, we can replace alpha with tangential acceleration over radius. That's regular linear acceleration over radius. And we've got it there. But now we can rearrange that and solve for tension. Part H, G. Here's the rest of G. Eliminate alpha, and find, this is the part where it gets crazy, the symbolic expression for the acceleration in terms of all the given quantities. In other words, what is this acceleration now that we have all this, but given in terms of the variables? Now, if we could just plug in the numbers, this would be trivial, but because we have to do it in variables, this gets intense. So here's what we're going to start out with. In place of the tension over here, I'm going to plug in, so in place of T, I'm plugging in the expression I have for T, or the tension, and putting it into this equation. That gets rid of one of the unknowns. Now if you notice, I've got just big M, small m, G, small r, acceleration, I, M, and A. You might say, oh good, we can stop there. Well, notice that I is not one of the terms that we have to have in this one. So here's where it gets intense. I'm going to try to solve for the acceleration. And again, this would be so much easier if we could plug in numbers. But please notice we have an acceleration here and an acceleration here. So before I can do anything, I'm going to move the green term to the other side. So now I've got both terms with acceleration on the same side. And yeah, a sub t is the same as regular linear acceleration, so I drop the t over here. Factoring out the a from this side, so I move the a out. I can't even draw around it. Outside of this expression, factored it out of both terms, gives me this. And I went ahead and plugged in I from up above. So this expression right here, because I can't use I in my final answer. So what's the acceleration? It's, once you solve this, we've got that. Rearranging terms a little bit, you can reduce it a little bit. Combining the mr squared here with the 1/2 mr squared gives us 3/2 mr squared. But that's about as far as you can take it. What's the acceleration? Well, just dividing both sides by what's here in the square brackets, you get this expression. Yes, that is hideous. But now that we have this, the rest of this is not so bad. But I'm out of room on this one, so let me move to the next page. We're on H. H states, all right, what's the numeric value? Whoops. Oops, that should be letter H there, not G. Well, we've got the expression right here. All we need to do now to get the numeric one is plug it in. It turns out big M is 2, small m is 1, small r is 0.04. And so we're just plugging in the values for all of these terms, and we can actually solve this numerically then. If you do that, you get this rather amazingly large formula, and you get this. So again, this should be H, not G. There it is. I asked for the tension of the string. Oh, sorry, that was the answer to G, sorry. And now for H, I'm solving it to get that. For I, if you look on the other page, tension is equal to IA over R squared. Plugging in, solving I real quick from the previous page, we knew I was equal to that. Plugging in our numbers, we get the rotational inertia of the yo-yo is 0.0208 to 3 sig figs. So we can plug that in down below along with the acceleration we just found over small r squared. and you get the tension would be about 35.4 newtons. Finally, J, how long does it take the system to drop 1 meter? For J, I'm using one of our old equations just from kinematics. Initial velocity is 0, so trying to figure out the time it takes to fall 1 meter. Delta x is 1, acceleration is 2.73 from up above, and if we solve for time, we get 0.857 seconds. Ouch! This was a long one. Hopefully that all made sense to you, and I hope I did all my math right. Good luck, and have a good